Okay, so I will present myself quickly, but so that's not me, right? So I'm here to share a story. So I didn't want to make a presentation with lots of bullet points or boring stuff. So I said, okay, we share a story. And this story is the story of this guy, actually. He came to the team a couple of months ago to do a master internship. Yeah, so this is his master work that we did together. So he is called Ignacio, but we call him Mega. Don't ask why. And I am Guiche. So this is, so I took last year, so this is the pronunciation in some phonetics, international phonetics alphabet, blah. So Guiche. Or if you're French or English, so it should be something like that, I don't know. So I'm working as a researcher in INRIA in Lille in the north of France. I contribute to Faro since 2010, around, I don't know, I was young. I'm not so anymore. And I do a lot of stuff. I realized that I have this thing of collecting hobbies. So now my new hobby is playing chess. So we also have, we have a little chessboard. If you want to play, we are going to contribute to science because Kyla, a PhD student, needs recordings of chess games. So if you want to play, we can play, record it. Okay, so what's the talk about? So I will start with this. Simple, so everybody knows, yeah, the syntax of Smalltalk of Faro, it fits in a postcard. And we can see the main features of the language, things that we love here. So actually the things that, okay, what can we see here? We see that we can send messages to execute user-defined operations, so yes. But we also have control flow, which are messages, and operators like math operators or Boolean operators. We have reflection also. Everything at the end is managed in the same way, yes? So we love to say that everything is an object. Well, actually, everything is a message, right? At the end, we have objects, but if we don't have the message, we cannot interact with them. So, and here I stole this thing from our object-oriented course in the university, so pretty basic. Everybody knows, yes, we have classes. And then if I have an instance of this guy here, I can send him a message. And what will happen here? Well, I need to find the implementation of this message, yes, a method, and execute it on top of this receiver. So what we are going to do is to find the correct implementation in this hierarchy and then execute it on top of this guy. So behind the scenes, what will happen is that we are going to look up the correct method to execute and then to apply that method on the object, yeah, with the arguments. So this is pretty basic. Everybody that ever implemented an interpreter knows this. So, okay. Now, what's the point of this presentation is that this lookup operation is very expensive. This is probably, so most of them, so the Smalltalk machines that we use, they are just popping and pushing values on a stack, moving some stuff around, and then this guy, it takes a lot of time. Yeah, so in the past, a lot of people have been working on how to optimize the lookup in particular. So I will bring this work from Peter Deutsch in 84, I think. So he was, so in this paper, he presents an implementation, I think it's the first implementation, that has JIT compilation and inline caches, yes? And the main idea behind this implementation is to reduce or to remove the interpretation overhead and the cost of the lookup, yes? So the idea is that we have if we have an interpreter that will just switch on the next instruction and do something, instead of doing this, we're just going to compile small methods that will just have the actual thing to do. So, okay, this slide this is pseudocode, bad pseudocode. Okay, so, and this guy actually implemented, so he optimized message send using inline caches. So, let's look that with an example taken from the open Smalltalk VM, from the Faro VM also. So here is how a message send looks in an ARM assembly. Yes, so the JIT compiler will generate this. So what does it mean? So it loads some value from x28 to x23, then it loads some PC relative stuff. Okay, no, let me translate that for you. So what's happening here is that, okay, those are two loads from memory into registers, and then we have a call, a relative call. Actually, what we are doing is loading the receiver into some register, and then we are loading the selector into some other register because we want to call the lookup routine with those two arguments, yes? So this is a very simplified version. So it's just to, okay, if you are not used to assembly code, this is what it happens. So you want to call this lookup routine here with these two things here. And of course, when we call the lookup routine, this will do something like that. So it will do the lookup, get the method to execute, and then it will invoke the method with the receiver that we have. Yeah. Now, this is what I call the unlinked implementation, because inline caches, what they will do is they will link this call site, this send site, with a particular implementation of a method. So what will happen is that we are going to add a cache in the middle, and this, when we are going to cache the result of the lookup, because we are assuming that probably here, doing the lookup many times, we'll find many times the same method. What will happen is that we are going to store the result of the lookup that is expensive directly in the machine code, yes? So what happens here is that this cache here, what it's going to do is to rewrite the machine code that is there, and it will change the load of the selector by a load of the class, and it will change the call to the routine of the lookup to a call to the method that we want to call, yes? So what is the idea behind this rewrite? We are writing the code dynamically, is that if we are loading this instance from memory, and this instance is of this type, then this is the method we want to call, yes? So, okay, pretty simple. Now, this thing is, I don't know, probably many of you say, well, maybe this doesn't work. What happens if this guy here is not of the right type? I am going to call the wrong method, and this is going to break. So actually what happens is that this linkage is speculative somehow. So we are going to call this method, and at the beginning of this method, we have a type check. Say, okay, I take this instance, I take this type, and if the type of this guy is the type that I specified, then we can continue. Otherwise, we need to call the lookup routine. We need to go and do the expensive lookup because, okay, what I put there was wrong, and we need to find the right implementation. So, this actually, so in the paper from Peter Deutsch, this worked pretty well. There were some some specific details that were different, but this is the main technique, and this is what we have mostly right now in the Faro VM, in the Open Smalltalk VM. So now, if you check how normal programs work, so I did it really. So this is not a serious benchmark. This is just to illustrate the issue. When you have a message send site, so a piece of code that does a message send, most of them, so I executed some benchmark for some time, and then I counted how many types I saw in a particular send site. So, and the number of send sites that have only one type, actually it grows. But we have a lot of other send sites that actually have more types, yes? So it can go actually from 2 to 7 in this graph. So we have cases where this simple implementation is not enough. And of course, since what I just showed you before is something from the 80s, later in the 80s too, or actually in the 91, I think, there was this paper where they said, okay, wait, sometimes types, so call sites are polymorphic. That means that I can find objects of different types. And with those different types, maybe I find different method implementations. So how does it work? Well, when I call the lookup routine for the second time, I know that I have a second type that I observe at runtime. And then what I can do is I can rewrite again this part of the machine code directly and put just a call to a dispatch table. And this little dispatch table is just a little switch written in machine code that will check, okay, if the receiver type is the one that I expected, then I will jump to this method. Otherwise, if it is this other type, I will jump to this other method and so on. Yes, and eventually, if none of the types match, we will call the lookup routine, that may manage the does not understand, that is the slower case, and okay. But the fact is, okay, the common cases are managed in this way. Yeah. So at the end, this is just a code patching state machine. Yeah, so we say, okay, I am in a state where I have observed only one type, so I patch it to that type. Oh, I observed a second type. Okay, let's patch it again to manage that case. Okay, I observed many types. Okay, let's patch it again to manage the many types, and so on. Now, of course, we were asking ourselves, this patching mechanism was invented in the 90s, so how does it work with modern hardware? And something that actually we didn't like too much in the implementation, we don't like, so the compiler has to write specific code that can be patchable. So we need to rewrite that code. So we need to know what is the code that is being written. And it cannot just be optimized out by the compiler. So also we need to be able to patch. We need to have different implementations of the patching per different platform for different, so for ARM, Intel, RISC-V, I don't know, think your own. And also, we are not only patching, sometimes we are taking decisions at runtime based on the shape of the machine code. So, look, if this call side looks like this, then I can't do that. I can do a context switch like this. Or I have to, I can collect this method that is taking space from the machine code cache and so on. So sometimes this is not, so it works pretty well. It has been working pretty well for like 40 years. So, but we wanted to think, okay, can we do something different? And that's where Ignacio comes, Mega, and he said, okay, I want to check how can we do table-based picks, yeah, polymorphic inline caches. So what is the idea? The idea is that we are going to change the message send for these pieces, this piece of code. So a message send will just be three similar instructions, three instructions like it was before. We are going to load the receiver, and then instead of loading some payload, we're going to just load the thing that we need to call a routine from a table. And then we are going to just call the routine that we learn from the table. And then each call site will have a table associated. And for example, if we want to have a monomorphic call, we have to have here the method. If we want to have an unlinked send side, then we have to call the lookup routine here, and so on. So this looks kind of like this. So on the left we have the patching mechanism. On the right we have the tables. Actually what happens is that on the right we have always the same machine code, but only the configurations of the table changes. So every time that we want to patch, instead of patching the machine code, we are going to patch the table, which is in the heap in writable memory. So it is much easier to manage and understand. So now, Mega did this. Let's say he did it in one afternoon. No, he didn't. But doesn't matter. So for this presentation, he did it really fast. Then he said, okay, how do I benchmark that? So he built a micro benchmark infrastructure to be able to measure what is the cost of doing the message send and what is the cost of patching without any noise, without garbage collections or any JIT compilations in the middle, no context switches. So so he was really picky on how to do that within the image itself and not doing it on the VM. And then, okay, we have this infrastructure. We run a couple of benchmarks and boom. So here what we have is, we have a lot of, so what we do is we run a benchmark for many times. And then what we do is we sample the time that it took to do some specific operation. So a particular sequence of message sends. And here we see that in the dark blue, this is the patching approach. In the light blue, we have the tables. And we see that it's on average 3 times lower. We say, okay, wait, what happened here? Yeah. Wait, so one thing is that Mega is a researcher, so he's a teacher assistant in the microarchitecture course in Argentina. So he was, okay, maybe these table picks are CPU unfriendly. How can we know that? How can we actually assess and how can we get better? So, okay, we run a profiler. And okay, and the profiler gives you a lot of information. What do we need to know to understand that information? So the first thing is, okay, maybe you remember from your operating system classes, or maybe, so Dave was showing this earlier in IWST. So memories are organized in a hierarchy, and on the top, in the CPU, the registers are faster to access, but they're smaller. And then you have main memory, disk, and so on. They are bigger, but they are slower to access. Okay. So things that we need to understand is that, wait, data is going to be cached in this hierarchy. So as soon as we need something, we are going to bring it from main memory to the caches and then closer to the CPU. But at some point, if we change some data, we need to invalidate those caches. And that means that we need to go back to the main memory and fetch it back. Yes, and we don't want that. We want actually to stay here close to the caches. So, of course, when I'm talking about data, it's not just the program data, but also the instructions. The instructions, they take space in the caches. So, and patching the code will invalidate the caches. So we need to refetch the instructions, and that the CPU needs to change the decision it's making. So now, so how can we see that? There are a lot of metrics we can take from the profiler. So here, for example, we have cache misses from the level 1 TLB, so loads, stores, the write back. So this is when we are writing the cache and it needs to go back to the memory and so on. And actually here the patching was slower. So it took more reads, so more cache misses than the table approach. So this doesn't explain the overhead. Yeah, so being slower, I don't care if it doesn't explain the problem. So we need to go a bit deeper. So for that, we need to the next thing we need to understand is CPU pipelines. So the idea is that instructions are executed kind of in parallel in the CPU, modern CPUs. So this is an oversimplification of how it works. So the idea is that executing an instruction needs to do different steps. And those steps, so for example, when the CPU is decoding some instruction, it can be fetching the next instruction. So we can do them in parallel. And now what happens is that sometimes when we have a jump instruction, if we don't know what is the next instruction, because we don't know if the jump will succeed or not, so if the branch, the conditional branch will succeed or not, we don't know which is the next instruction. Maybe we will know what is the next instruction when we finish executing the jump instruction. So that means that before finishing the execution of the jump instruction, we cannot actually execute anything. So we have to wait this to finish to be able to execute something else. So this makes that the CPU is kind of idle, doing nothing for some time. And this is what we are calling, is called stalling. Yeah, the CPU stalls some cycles, so it's doing nothing. There are many reasons for stalling. Bad data dependencies, I know. But jumps are one particular problem. And of course, the CPU has mechanisms to cope with this. For example, the most common one is what is called branch prediction. So what is branch prediction? It's that the CPU tries to guess. Say, look, I have this jump. I am fetching the instruction, but probably you want to jump there. So I will start treating the instruction, and if I fail, so if the jump actually didn't jump that way, if I guess wrong, well, I'm going to just discard everything that I did. And okay, I lost some time, but maybe I guessed right. And the fact is, okay, maybe, so how can we help the CPU to guess right? So and here we see the counters in the CPU, and we see, for example, different kind of mispredictions. So branch mispredictions, indirect mispredictions, stalls, and these indirect cause mispredictions. So and here actually we are kind of slower. So this could be the thing, yes? So the table approach has more mispredictions than the patching approach. So now, why is that happening? So if we check the patching approach, what happens is that here we have the implementation for the unlinked monomorphic and polymorphic calls. And okay, maybe we don't know where we want to jump, except that here we have the actual place where we want to jump. So here we have a direct jump, a direct call. So we are telling the CPU, okay, I want to go this place. You don't need to guess. So here we have an absolute address. So yeah, of course, if we know where we are going to jump, then the CPU actually it doesn't need even to guess. So now, if we with this kind of learnings, what did we learn with Ignacio is, okay, these peaks, these patching peaks, they are good for branch prediction. They are have a bit of bad cache behavior because they need to update and that invalidate the caches and also it has this portability issue and maintenance, so they're a bit messy to maintain. So can we do better? That was the question that we asked ourselves. So what is actually problematic with our implementation? So just if we look at the implementation of the patching peaks, what happens is that each call site will have associated its own piece of code to manage the polymorphic case. Yes? But when we take a look at the table-based one, actually they have, each of them, they have a different table, but they are sharing the same machine code. So actually the problem is that maybe the CPU, when it's executing this guy, doesn't know if this guy is going to call some method or many different methods. So it cannot actually realize that we are in different paths in the execution. So, okay, what we can try is to duplicate that code and use different call routines for different call sites, kind of what happened before. Some simple experiment that we did is that, okay, what happens if instead of just, so we are going to add a lot of these in the VM and assign them, allocate them randomly, so using some round robin strategy to each call site like that. They are kind of distributed, their usage. And actually, with this, just doing that, took down the execution of the same benchmark from 3 times to only 30% slower. Yeah. So I am already in 21 minutes, and this is actually where we are now with this experiment. So Mega is still working on this, but what are kind of the takeaways that I would like to share with you today? So we are actively making the VM easier to maintain and to change and to support. We are looking for simpler implementations that give us the same performance output, but sometimes we need to help the CPU, so we are still in the fine-tuning phase for this particular thing, but we are doing this all the time for everything. So thank you very much. Questions? Coffee. Yes, Philip. I can make it available. It's not yet. But yes, we can do it after. I have to ask him permission first. But yes.
Yes, I would also like that. I also wanted to thank you for a much clearer explanation of the stall and cache problem than I had in my text-only talk yesterday. This is really quite interesting because I have been working on how ZAG is going to work with, is going to handle picks, and I think I'm almost to the point where I think I only need the monomorphic case, everything else, because I have a very fast dispatch. However, I had not thought of, and I appreciate this, the fact that if you're calling a common routine and that routine is doing some kind of lookup and then branching, then that's where the branch prediction is going to be attached, and it's going to be completely wrong almost all the time because it's all coming from the same. At that instruction there, it's all, it's going randomly for all intents and purposes.
Yeah, the fact, so here it's not clear, but the fact is that this guy has the actual jump.
Yeah.
And if this guy is shared, then that means that it shares the cache for all of the potential callers. So the guy is going to mispredict every time. Yes.
Yeah. Wow. Thank you for screwing everything up. Appreciate it.